Today we continue our work on differential calculus. During our previous lecture, you acquainted with the ideas of the compound function. And today we try to make some examples of the differential calculus for different functions. So it's kind of a practice work now. But firstly, I have to give you the rules of the differential, or the differentiations. Remind you rules. So, if you remember, we denote, so if y equal f of x is a given function, we denote derivative of the function like fy prime or f prime of x, or we can use these denotion df of x over dx. So here we have prime of x, prime of x, this, or df of x over dx. We can use this notation or this notation, it doesn't matter here about differential calculus. And we have some examples, some rules here. So if you have addition of two functions, the derivative of the addition is addition of the derivatives. So you can calculate them separately. If you have multiplication by number, a is a number, constant here. So I can take a array the differentiation and differentiate only function as itself. What else we have? If we have product of two functions, their derivative is a summation of the kind of cross product, cross primes. So here you have firstly calculate derivative of u, and then add and multiply by v plus u multiplied by derivative of u. What else do we have? Some people use the derivative of the division, but I don't care about it because I usually add up derivative of the division to derivative of the multiplication. And the first one rule here is about compound function. If f of g of x is a compound function, we firstly have to calculate derivative of f with respect to g times derivative of the g of x. This rule is the most confusing for students. And we make some examples firstly, some easy examples to remind you how to calculate derivatives. And then we go into the derivative or the calculation of the differentiation of the compound function. And you will understand why I gave you before the concept of the compound or composite functions. So here we have some piece of theory. I try to use only this space to calculate the different examples. And I start from the very easiest situation, then I have addition of two functions. Examples. For example, we have sine x, the first one, plus x. It's a given function f of x, and I have to calculate derivative of these functions. It's sine x plus x derivative. Oh, I'm sorry, primes of x here. You can notice that we have here addition of the functions, or we can use the first one rule. And it is sine x derivative plus x derivative. As if you remember, the table the elementary function I gave it before to you, we have derivative of sine, it is cosine x, derivative of x is just 1. So we can say that derivative of this sine x plus 6 is a new function which is cosine x plus 1. The second one example. For example, we have x squared plus 3x plus x times cosine x. This is the given function f of x, and I want to calculate derivative of the function f of x. F prime of x equals, I have to write down this long expression within parentheses 3x plus x times cosine x, and put here prime. That means that it demands the derivative calculation, is still waiting for all of these calculations. Now you can notice that we have here additions of the function. X squared is added by 3x is added by x cosine x, and I use the first one rule here. It is x squared prime of x plus 3x prime of x plus x cosine x prime of x. Now you can see here x squared. I remind you one more time that we have the elementary function, and here you have the rule, it is 2 times x squared minus 1 plus 3 times x. You have here a rule that if you have multiplication constant by some function, you can take constant beyond the derivative calculation, so it is 3 times x derivative. And the last one here, we have product of two functions, product of x times cosine x, and you have to expand this derivative using the third one rules here. We have when we have product or multiplication of two functions plus x derivative times cosine x plus x times cosine x derivative. Now we have 2 times x derivative is 1, x derivative is 1, so I have just cosine here. And the last one, x, cosine x gives derivative minus sine x, and I have x times minus sine x. This is the result. I can put this minus instead of this plus, but it doesn't matter, so we have 2x plus 3 plus cosine x plus x minus 6 times sine x. So we have two examples here. Two examples. I will share with you this one print screen. First two examples show that we can use the first two rules here and add given function to multiplication of functions, or multiplication by number, or summation of something. Or even I can use here not even minus plus, but substitution, subtraction, plus or minus. So we can use for subtraction and for addition the same rule, the first one. But for example, I give you here the third one example. So the given function f of x is sine x squared, and I want to calculate the derivative of this function. So f prime of x is unknown thing here. So firstly, I have to write down the thing sine x squared prime of x. But what is the difference here between sine of x squared and just sine of x? The difference is that this function is a compound, a composite function. You can notice that to calculate sine of x squared, you have to make two operations. Firstly, you have to raise up x to the square, and the second one to the second power. You have to transform x. Firstly, you transform into x squared, and then x squared you transform into sine of x squared. So it's think that mapping sends x firstly into x squared, and then the other mapping sends x squared into sine of x squared. I can denote this operation like g of x. So g of x, I put here g equals g of x, and it is x squared. And then I have other function f of g, which is sine of g. Or simultaneously I can write it like sine of x squared. So you can see that we have two operations. One more thing I said, I want to underline it. I want to dwell your attention on this circumstance. Firstly, we have to calculate x squared, and I denote like g, and then we have to calculate the sine of this g. So we deal with the compound function, and now I can denote this f of x like f of g of x. So this is the compound function. It's given like in this example. So it means that firstly I have to calculate derivative of this f of g. So I want to f of g, so the external part. So here we have like opposite chain. Firstly we have to calculate x squared and then sine x, but here I firstly have to make the external part f derivative, and then multiply by derivative of this internal part g of x. So you have to forget for a while that you have x squared here, and put instead of f prime of x derivative of the sine, and you have to leave this argument here, and it gives you derivative of the sine gives you cosine x squared. I want to, with respect to g here is x squared, cosine of x squared times, and g of x is x squared, derivative over x squared. And you have finally derivative of x squared, 2x times cosine x squared. This is the very confusing thing here. So I don't know if it is clear or not, but firstly when people face these kind of examples, they are very confusing about this calculation. They can't distinguish them. What is x squared, what is sine here? But to understand it more clearly, I give you one more example. Another one. An example. F of x equal 1 over 1 plus x. And I want to calculate the derivative of this x thing. Is unknown. Okay. The first one thing here, we have to identify is it composite function or an elementary function. You can notice that we have two operations here. The first one, g of x, mapping sends the x into the 1 plus x, and the second one, operation, which is it f of g of x, it sends 1 plus x into the 1 over 1 plus x. So we have here two operations, and that's why consequently we have used to this rule of the compound function. So if I want to calculate g of x, by the way, I used here a capital letter. Here I use a small letter. It doesn't matter because it does the question of notation. So f of g of x is, firstly I have to calculate the derivative of this thing with respect to g, and then calculate multiply by derivative of g of x with respect to g, with respect to x, g prime of x. So I denote like f of 1 over g derivative plus derivative times derivative g. So here I have g raised to power minus 1 derivative, and here I have derivative of g. You remember this formula maybe, that the power function with the power n gives you n times x n minus 1. So we have minus 1 here, so and it is minus 1 times g, and minus 1 times g prime over x, and it gives me minus 1 and minus 1 minus 2, and minus 2 I can put it g into numerator, and I have 1 over g squared times g prime. Now I can make substitution. Instead of g, I know that g it is 1 plus x. So I have minus 1 over 1 plus x squared times 1 plus x prime of x. And it is minus 1 over plus x squared. 1 plus x, 1. Derivative of the constant gives 0, derivative of x gives 1, so it is times 1, and the final result it is 1 plus x squared. Or squared beyond the brackets. 1, 1, 1, and 1. So here you have the other one example, 1, 1. 1 here, because I don't want to mix this prime and 1. And this 1 and 1. And 1 here. Because we have prime here, and we have to have here unit notation. And here I have like primes, so they are ones here. So we have this example here. I give you example of this function. F of x equal a trigonometry function f of x equal tan of x. And I want to calculate derivative of this function f prime of x, tan of x. Right. Okay, tan. At the first glance, it is an elementary function. But really, people, they don't remember the derivative of the tan. I can say that it is 1 over cosine square of x. If I remember, it's quite good. So if you don't remember the derivative of the tan, you can use this one approach. We don't. So I can express tan through sine and cosine x from trigonometry. Sine of x over cosine of x. and derivative here. It's the same thing like sine x times 1 over cosine x derivative. Now you can compile this one expression with the rules, and you can notice that we have product of these two functions. And it gives sine x derivative times 1 over cosine x plus sine x times 1 over cosine x derivative. The first one term here is very easy to calculate if you remember the derivative of sine gives cosine x, and you have cosine x times 1 over cosine x plus sine x. But here we have composite function. Firstly, we have to calculate cosine x, and then we have to calculate divide 1 over cosine x. So this one is cosine, and I want to raise it up minus 1 and define these prime of x. What else do I have? I can cancel here cosine and cosine. And I have 1 plus sine of x times we are Russians and we are very keen on parentheses. Okay. Oh, cosine minus 1. So firstly we have to calculate cosine, and then we have to calculate minus 1. So we have to start from the last one operation and consider the cosine x raised to power minus 1 like a power function. And if you remember, we use for power function this formula. X raised to power n derivative of prime of the x gives n times x n minus 1. So power here n is minus 1, so I have minus 1 times cosine x minus 1 times by derivative of the first operation in the chain or the composite function, cosine x derivative. And finally I have 1 plus, no, don't plus, minus, I can put before sine x, cosine minus 2, it is cosine minus 2 of x, and cosine gives you minus sine. Derivative of cosine minus sine x. And we have minus and minus plus sine times cosine sine square x. Cosine with power minus allows me to turn this cosine x into the numerator and put it here cosine squared of x. Okay. Now we have here to addition of the number and a fraction, and the common denominator is cosine squared. So it is cosine squared plus sine squared over cosine squared plus sine squared x over cosine squared of x. If you remember trigonometry, you can notice that cosine squared x plus sine squared is 1 if they have the same argument as an angle, and it is 1 over cosine squared x. So If you check this result in some math books, you can notice that derivative of the tan is exactly 1/over cosine squared. Some people say it, I don't remember exactly, a cosecant function. But I don't like very cosecant function because they don't make any new sense, and I use cosine squared. Okay. So what is the bottom line here? How do you think? So firstly, I want to clean everything here, and then I make some ideas. I define some ideas. So what is the bottom line, or what is the main idea here? Maybe I don't know, maybe it makes easier your calculation. But if you have a compound function, a composite function, I put here especially f of f1 of x, f2, f3, f4, f5 of fn of x, and it means that you have calculate derivative of f with respect to f1 multiplied by f So what is the bottom line of these examples? For example, let's consider this one formula. F of g or fix derivative. So the first one thing, you have to calculate derivative of the f capital with respect to g. Then multiply derivative of the g with respect to x. If you have a chain of the functions, of three functions, and you want like g of f of x, you have to calculate f with respect to g, then multiply g with respect to f, and then multiply f with respect to x. So you have to expand this function f prime of x here in order of these function. Firstly, I have to the external part f of g with respect to the function g, and then g with respect to following function f of x. If you have four functions here, the derivative calculation demands you to calculate f with respect to g, g with respect to h with respect to f, and f with respect to x. Always you have to expand your given function. So, today I give you some home assignment. I put it over there. Try to make your home assignment at home. If you can't cope with difficulties, ask me, and next hour work I can dedicate to this calculation. So home assignment. Assignment to do. Calculate derivative of the cosine x over sine x. Prime of x. 1 over 1 plus ln of x. Cosine x, cosine 1 plus x squared plus over 1 plus x squared and here squared. I think it's enough for a while. So here you have your home assignment and you can ask me your questions, and our next topic will be dedicated to some issues or challenges when we are working with investigational functions. But if you are failure at this calculation, we can take apart these examples to calculate them. I want you to be clear in this one topic, because this topic is the most important topic about differentiation. See you later. Bye bye.